Hey, geometry, Mr. Mitchell, and this is my first video of 2021. So, belated Happy New Year. We can do this. We can do this. We've been studying triangles still. Maybe you're getting that feeling. You're like, whoa, this triangle thing. I don't know. What is all this about? I'm just gonna get myself out of the picture. I want you to read my favorite Christmas present this year. Apologies to my classroom who's already read it, but here you go. Picture in the middle. Education is not the learning of facts, but the training of the mind to think. And training you to think, that's what I think the most important part of geometry is. Will you go on to college and major in triangles? No. Will you go on to trade school and become a triangle technician? No. Well, maybe if you were a roofer and you built trusses by hand, but you're probably not going to be a triangle technician. What we're trying to get you to do is learn to take your math from one dimension to two dimensions. Analyze a problem, solve the problem. Learn to think. Figure out what kind of learner you are. Take in new material, consider it like a problem. That's worth knowing for the rest of your life. Figure something out you've never seen before. Analyze it, come up with a solution to your problem. That's what you'll get out of high school geometry. Okay, here we go. I'm going to take my picture away. And let me just orient you to the one page that we have for notes. If I zoomed out, it looks like this. Okay. I'm going to talk about the top and the bottom, a couple of new terms here. Has to do with triangles. And then I'm going to show you some examples. Okay. Orientation. The classic look of the notes in geometry class is they give it a theorem. And this is the centroid theorem. So this is a vocabulary word, and it's going to be a piece of a triangle here. The centroid of a triangle is 2/3 of the distance from each vertex. Okay, vertex. And as Mr. Scott pointed out last week, a vertex is an angle to the midpoint of the opposite side. So let's look at that in the picture for you visual types. From a vertex here, which is angle A, to the midpoint of the opposite side. Okay. Centroid. 2/3 of the distance from each vertex to the opposite side. Vertex to opposite side. Vertex to opposite side. Okay, what they're saying is this is 2/3 of the distance, and this is 1/3 of the distance. This one has the majority of the length over here, so this one is 2/3 and 1/3. And this one is 2/3 and 1/3. And I'm just showing you fraction of the distance from each vertex to the middle of the opposite side. For math examples, we will go through these. Okay, so between this definition, the one at the bottom here, and these examples, your entire assignment and big ideas can be taken care of. There's a little piece of review on the topics that we studied last week on angle bisectors and perpendicular bisectors. A little bit of review on some terms, but primarily the math involved in today's assignment is going to be here. Okay, so the other big that we're covering is the orthocenter. Okay, the orthocenter. The lines containing the altitudes of a triangle are concurrent. This point of concurrency is the orthocenter. And in this picture to the right, they show the altitudes of a triangle from a vertex to a 90-degree angle with the opposite side. I'll show you a little better definition in a bit, but orthocenter and altitudes have to do with drawing a line between a vertex for the triangle and the opposite side, and this time it makes a 90-degree angle. It doesn't just go to the middle of the opposite side, a 90-degree angle. We're going to look at a demonstration and kind of just, you'll watch me tinker with some triangles. We'll come back to these three problems and we'll be done. Okay, so teachers, if you would, make graph paper available for those in class who will follow along. And I'm going to put up a template. If they'd like to follow along in making a triangle with me, they may. Or you could try just absorbing what's going on in this image. Here we go. A median. Here's a little cleaner definition. So I'm putting this on my graph paper. Medians are the segment from a vertex to the midpoint of the opposite side. So I'm a visual learner. I kind of need to see what this looks like. I did not plan out this triangle except to make two of them on the same page. And when I chose my points here haphazardly, I measured the distance in millimeters and I put a halfway mark between each of the points. So I measured in millimeters and put a halfway point in the middle. Okay, so if a median is what it says, let's see what it looks like. We're going to draw a line from a vertex to the middle of the side. That makes these congruent. Okay, now we're going to see a little bit of a pattern here. I'm going to do it again. A segment from a vertex to the middle of the opposite side. And that would make these congruent. And starting to get a little look to it. One more time. Vertex to the middle of the opposite side. And how about that? 3 points. It works with any triangle. And here at whatever this coordinate would be, that is my centroid. And I'm going to call this C. And just below, I'm going to say that point C is the centroid. Okay. So now you've seen a textbook definition of what this is, and then you watched one built. So these lengths are congruent. That's kind of a neat symmetrical pattern to it. And if you draw a line between the vertex and the middle of the opposite side, do that 3 times, those lines will all cross, and they'll cross in one place. So this is a concurrence. They are concurrent lines. They cross at this spot. Okay, so like I said, I did not plan specifically this triangle, but I did go through and make sure this theorem works. So a theory, we ought to be able to collect evidence to support it. That's what they say in the scientific classes, okay? So when I measured this guy, all right, and you got a little bad glare there. Okay, for the moment, the length of this line from one to the other, let's see, it looks like 0 to 90 millimeters. 90 millimeters all the way across. And check it out. Here, where the centroid is, that's 60 and 30. 60 millimeters and 30 millimeters. Aha. The centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. Vertex, 2/3 of the way across, which is 60 out of 90. That's where the centroid is. It works with a drawn triangle, and whatever triangle you have, if you're following along, it should work pretty similar. Let's look at this one. Okay, so that's about, somewhere in the neighborhood of 70. 70. Okay, so if I get a tight measurement there, this looks like 23 millimeters. And let's see how long this one is. 46 millimeters. Did the theory hold up? It did. 23 times 2 is 46. This is 1/3 of the total length, and this is 2/3 of the total length. And if I put those together, oh my gosh, I'm nervous. 46, 56, 66 plus 3, 69 millimeters all the way across, or almost that 70 that it looked like in the beginning. 69. All right. I checked this one before we got started. I had 24 millimeters for this length, and I had 48 millimeters for this length. So with a haphazardly drawn triangle, we have demonstrated the centroid here. 2/3 of the way from a vertex to the opposite side. That's where these lines will cross, going in that direction. We'll use that math in a demonstration. But I want to give you a little bit on the altitude of a triangle because we're going to use this again this year. Okay, so I'm moving down to the same image. I just made sure that my spacing between the lines on the gridded graph paper were the same. And I'm going to try to draw altitudes. An altitude is a perpendicular segment from a vertex to the opposite side or to the line that contains the other side. Okay, so I'll demonstrate that in a second. If I want a 90-degree angle, so it says perpendicular segment from a vertex to the opposite side, I am going to need a 90-degree angle on this opposite side. I'm going to work from this vertex, so 90 degrees. All right, I put the crosshair of my protractor just so until I get this guy, dropping a 90-degree mark here to there. So I've measured a 90-degree angle, and this should look like a 90 if we back off. This looks like a perpendicular intersection. I think I could buy that. But let's try it again. I'm going to put it on this side, line up perfectly on this side of the triangle, and then point my 90-degree angle at the vertex opposite. Oh, that's pretty close. Pretty close. I'm trying to draw a 90 from here to the line, and I think it looks about like that. So this should line up so, to there. We'll have to disregard this one. That is an extra line that I drew by accident. Okay. So we are dropping, they'll say, dropping an altitude from a vertex perpendicular to the other side. We will need this when we do the area of a triangle. That's why we spend a little time on this piece of vocabulary. We need to know what an altitude is to calculate the area of a triangle. There's one drop to the opposite side. So we need one more. Okay, a 90-degree angle from this side now. And line it up on there so it's sitting on top of the line segment, and it points directly at a 90-degree angle to this point on the triangle. So I'm going to add a point there. And this should be the last altitude. And if it works right, these three lines will meet at a point here. I'm going to label this O. And point O is the, big word, orthocenter. The orthocenter. A description of the point where the altitudes will meet. And we just drew altitudes from a vertex to the opposite side, a vertex to the opposite side, a vertex to the opposite side, and those three lines crossed right here. And this is the orthocenter for our triangle. Different than the centroid, this is the same triangle. I copied it down below, and you can see if we look at both of them at the same time, centroid is there, orthocenter is there. Okay. We will not study the mathematical ratio in the differences of the line segments in here. We need altitude to understand area of a triangle. Okay. I want to show you one more thing about triangle and an altitude. Sometimes you have an obtuse triangle. Okay, so I'm going to create an obtuse triangle here. That means it has one angle that is larger than 90 degrees. Okay, so haphazardly, I've just chosen some points. I've made an obtuse triangle. This angle here, whatever it is larger than 90. And the altitude for this triangle, if you're considering this vertex, you have to drop a line that ends up outside of the triangle. This would be the altitude. If we needed this measurement to calculate the area of a triangle, the altitude was dropped out here, outside of the triangle. That is the line that comes from this vertex and lines up with this segment on this end of the triangle that makes a 90-degree angle. The altitude can be outside of the triangle. Outside the boundaries of a triangle. Okay. I'm going to pause here for just a second. I hope these examples were kind of helpful. I will put a copy of this out so you guys can look at it. But I urge you to draw a triangle for yourself and then just attempt to do these things. Draw from the vertex to the middle of the opposite side. You'll have to measure to see where the middle is, or use a protractor to draw from a vertex to the 90-degree, to the opposite side where there's a 90-degree mark where they meet, a 90-degree angle. Okay. I'm going to flip back to the page for notes that was handed out. Here we go. Now maybe this makes a little bit more sense. The centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. And we looked at some measurements, some true measurements that help us. Okay, and so now we're going to look at what we'll be asked to do as far as the math. The fraction helps me kind of set this up here. The medians of triangle ABC meet at point P. Point P is in the middle. So A to P here is 2/3 of the from A to E. This is 2/3 and that's 1/3. So let's look at these three exercises. Point P is the centroid of triangle LMN. LMN. Okay, so there's LMN in the corner of all these triangles. P is the centroid, and they use the same letters. All right. If QN, okay, so it's different measurements for each. If Q to N, this distance is 33, find PN and QP. Okay. So if QN equals 33, then, okay, the centroid, 2/3 of the distance from the vertex to the midpoint. So PN should equal 2/3 times 33. Multiplying fractions. Maybe it's been forever since you did this. Since this is a single number multiplied times a fraction, I'm going to multiply it times the top. 2 times 33 divided by 3. That's equal to 66 divided by 3, 22. PN is equal to 22. So if PN is 22 from here to there, and QN is 33, by subtraction, we can do the other. QP is equal to 33 minus 22, or 11. And maybe you see a pattern here. 33 is the entire length, 22 is 2/3 of it, 11 is 1/3. So here, in number 2, if Q to N is 45 units of length, 2/3 of my length are here from P to N. What's 2/3 of 45? See if you can do it. What's 2/3 of 45? Shout it out. You at the back of the class. Yep. That'd be 2 times 45 is 90 divided by 3. 2/3 is 30 units of length. And that would leave 45 minus 30. So Q to P is equal to 15. 30 and 15 would come back to our original 45 measurement. Q to N is, this is on number 3, 39 units of length. Okay, I'm trying to do it. QN is equal to 39. Oh, I guess this teaches me how to think. So what's 2/3 of 39? That's, I can think of a number that divides into that. QN is equal to 2. Oh, no. Sorry. PN is equal to 2/3 of 39. Okay. 2 times 39 is 78. 78 divided by 3 should be 26. Leaving 39 minus 26, QP is equal to 13. All right. Patterns here. I'm just going through and picking out the numbers that we calculated. Full length is 33, 2/3 is 22, 1/3 is 11, etc. 45, 15. What do we want you to do today? Not become an expert in triangles. We want you to learn to think. You have to work with new vocabulary. You have to think in two dimensions. The centroid of a triangle, you'll find the mathematical problems deal with this. But big picture, we've just described some other features of triangles. The centroid describes this point in the middle, and it is where the medians cross. The medians from a vertex to the midpoint of the opposite side. And the orthocenter is where the altitudes cross from a vertex to a 90-degree angle on the opposite side. Not the midpoint, but a 90-degree angle. I hope that gives you enough to go on. You have a reasonable length assignment in big ideas. Good luck and have a good rest of your day.